Going live in 3, 2, 1. Now! Let's see. Waiting for YouTube to update the screen, and right, so we are live on this screen. Let me just move things around a little bit. So, in this series, in this series of videos, I'm going to be building a motor driver with two brushless motor outputs and current limiting and brake output and all the things that you can wish for in a motor control circuit. And it's also going to have both the CAN bus, which is kind of ubiquitous, and it's going to have EtherCAT, the Ethernet-based control protocol that goes over the Ethernet layer and provides really good, really high-speed communication from the control PC to the motor control unit. So this motor control unit is going to have EtherCAT, which is going to be very useful for high-speed control. Let's get started by making a little diagram of what it is that we're going to be building here. So I'm going to go ahead and open DriveIO, where I've created motor drive XML. Okay. Let's see. So we're going to have control unit, which is going to be STM32 chip. That is the main CPU that I'm going to be using, and this CPU is going to be controlling driver of the MOSFET driver chip. And for the MOSFET driver, I'm going to be using DRV8302. I've used other MOSFET drivers before, but since I started using DRV8302, I have been happy ever since, because this chip is absolutely amazing. It has everything that that you need for motor control, for driving a power stage. So it's not for the motor control, it's for driving the power stage, and it does its job really well. So it has automatic overcurrent protection. It protects the outputs from short circuit. It has a variable current setting. It has. Let's actually pick up the datasheet of this chip, so we can see exactly what it has. DRV8302. And by the way, I'm using incognito tabs so that you don't see the type of porn that I'm watching. Let's see. So this chip is able to drive MOSFETs, a three-phase H-bridge with a current of up to 1.7 amps, which is more than enough for what we're doing here. The current is going to be determined by the size of the MOSFET, by the gate capacitance of the MOSFET. So the more gate capacitance, the more current you will have to push into the MOSFET to get it to switch quickly. If we have lower current capacity on the driver side, then we're going to have slower switch times for larger MOSFETs. So picking a driver that has sufficient current capacity is important in order to be able to achieve high switching rates. For this circuit, I'm probably going to be using somewhere between 30 and 40 kilohertz switching rates for the PWM that drives the MOSFETs, which generate the three-phase sinusoidal waves that drive the motor. And I also want to have 48-volt operation. So this chip is perfect because it supports up to 60 volts operation. It has protection. It has programmable dead time control, which is very good for ensuring that the MOSFETs don't get hot. Because when you switch from the high side MOSFET to the low side MOSFET, there is a a small period in there where both MOSFETs can be on, and that heats up both MOSFETs, because then you have a short circuit going from the power supply to the ground. And even though the time is very, very short, it can still generate heat, and that's undesirable. So having programmable dead time control is very good. Programmable overcurrent protection. This chip controls overcurrent protection by setting an analog value that sets the current limit, at which point the chip will just power off the bottom side MOSFETs and only drive the high side MOSFETs. And once the overcurrent situation is gone, the chip will continue to drive MOSFETs as usual, so you will get uninterrupted operation. And it also has an overcurrent output, which signals to the MCU that there is an overcurrent fault. We have VDD overvoltage lockout, which would happen if the power supply side rises above the rated value for the input voltage of this chip, which can actually happen when you're driving a motor. If the motor is braking, it's going to be generating electricity, and that will rise the voltage on the power rails if there is no place for the energy to go. So the power lines can rise almost arbitrarily unless there is protection, which we're going to build into this. We're going to build in extra protection into this circuit, so that our our voltage levels never rise beyond a certain over voltage maximum point. We have over temperature protection or warning shutdown. We have and all of this is reported through the fault pin. Typical application is three-phase BLDC, pumps, e-bikes, power tools, robotics, RC toys, industrial automation. So a fairly well-designed chip that has everything that one can wish for in terms of driving a power stage. So this is the chip we're going to use. We can put this into our diagram here. And then we're going to have a motor that's going to be connected to this chip using 3 wires. This would be a BLDC motor, and it's going to have arrows going, let's see, like this. Can we get a line that is just a straight line? Yeah. Actually, I could just probably do it like this. Okay. Yeah, let's make this a straight line. Oh, what is this? Oh, we can have an S-spline. No, that's ugly. Use a straight line. Straight line like this. And then we have the 3 phases. Go to the sorry, this is actually going to be the MOSFETs. This would be the MOSFET bridge, which will be driven by the DRE chip. Come on, make this a little smaller. See if I can make this smaller and get the lines relatively straight so it looks good. So copy this, and in front of this we'll have the DRE chip, and from the motor we are also going to have encoder input, which will be implemented using another chip that is specifically designed for different types of encoders. So the way that typically encoders are implemented on these motors, and it's different for different motor. Sometimes you get a differential encoder output where the motor is going to output just the encoder pulses, but it's going to be a differential line. So there will be like a for A, there's three outputs from the encoder, which is A, B, and Z. AB determines the direction of the, it's basically the encoder pulses, they determine direction and the speed of the encoder, and Z is the 0 point. So every time the motor spins past the 0 point, the encoder is going to output a pulse on the Z output. And if this would be a differential input or differential output from the motor, then we'll have to have a differential input on our PCB in order to be able to read those encoder pulses reliably. So there could be a cable that is maybe arbitrarily long from the motor, which may put, if we have a differential interface to the encoder, we want to take advantage of the differential interface. We don't just want to use the positive wires to get sort of the single-ended input. We want to use both of the positive and negative for each line. So we want to support that, and that is usually 5 volts. But then there could be an encoder input that is a single-ended, and it's probably pulled up to 24 volts, and it's then shorted to ground by the internal circuitry of the motor. So we have to support 24 volts on the single-ended input. And designing all of this manually would be fun. I would use maybe a multiplexer, and I would use input protection diodes to along with the series resistors to clamp the input voltage. But why do that if there is ready-made solutions for this kind of thing that work really well? So I'm gonna go ahead and look up the chip that I will use for this, and it would be, let's see, it's some Max chip, but I don't remember the number of this chip. Let's see, encoder input, encoder input IC. Could this be something? Max 14890. This chip supports all the different varieties of encoder interfaces that are available on the market. So we can support both RS422, which is the differential lines. We can have the single-ended lines, and the DHTL is let's see, DHTL. What does that stand for? It's one of the alternatives I've never used. Differential HTL, max and different. Right. Okay. I'm always curious about something when I see something that I don't really recognize. Let's see. So can be configured for DHTL operation. Input signals up to 40 volts can be accepted in the DHTL mode. In pin control mode, set the blah blah blah. Yeah, truth. Yeah, just so let's see. In SPI mode, each of the receivers can be individually enabled for DHTL functionality. Well, that's good. So this chip connects to the microcontroller over SPI, and we can configure each of the receivers inside this chip for the desired mode. So let's go back to the beginning here. We have the circuit of this typical operating circuit, where we have the encoder from the motor, and it connects to the input of this IC, and we have our ASIC or microcontroller up here just communicating with this chip over SPI. And as the outputs on this from this chip will get, I think, 3.3 volts. Let's just make sure what this. Let's see, supply voltage 5 volts. Okay, so we have 5 volts output. That's good to know. We'll just have to possibly level shift it to 3.3 volts. But at least we don't have to deal with 40 volts input voltages in this case. I'm just gonna check the pinout of this chip just to see what it's how it needs to connect. So let's see. So it seems that, yeah, we're gonna have to have this little capacitor and resistor there. And we have 3.3 to 5 volts. Okay, so this chip has a special VL input, which is the interface voltage, which can be 3.3 volts. The VCC is 5 volts, but the outputs can be driven by 3.3 volts, which is very good. So no need for any level conversion on the outputs. And yeah, and the outputs will be just so we also have extra inputs here for things like proximity sensors and possibly other peripherals that can be on the system we're trying to control, which will be outputting high voltages like 24 volts, for example, for a zero sensor that will fire whenever whatever is controlled by the motor reaches the 0 point. So it's very good to have a few extra inputs that we can use. Let's put this in the diagram here. So this would be Max, and I can't remember the name, Max 14890. Okay. 14890 will connect to the encoder. Let's see, we can put it here. And then we have let's do this, change the form of this arrow. So we have Max 14890 encoder interface. And there is also going to be possibility to connect sensors like proximity sensors to this interface. So I can, let's see, can I move this arrow? Move this arrow a little bit here. Come on. Oh, this is really annoying. Now the arrow is, oh, okay. That's better. So we'll have two extra inputs for this proximity sensors, which will be connectable to this same interface. So this goes there, and this connects. Can I connect two arrows together? Yeah. Let's just do like this. And that messes up my arrows. God damn it. What if I do like this? Cut and paste, and then move it in place. That doesn't mess up the arrows. That's good. So this will connect directly to the STM32. It's going to go to the timer inputs that are responsible for reading the encoder counts. STM32 has built-in hardware, by the way, that supports encoder modes, so that we don't have to interfere with any, we don't have to implement the reading or the interpretation of the encoder pulses manually. The timers take care of that. Then we have the, let's see, I'll delete this arrow and just move this block a little bit closer here. Let's see. the arrows can be a little bit misleading here. Like, is it the motor that connects to the MOSFET power stage, or is it the power stage that connects to the motor? So just ignore the arrows. We can actually do like this even. So I'll just change the appearance of this arrow. None. That's better. So no arrow. That's better. We also need to have a brake resistor output, which will be implemented by a MOSFET that will short the power supply lines over the brake resistor. So whenever the voltage on the power supply lines goes beyond the maximum set voltage, we will short the power supply lines and dump that energy into the brake resistor. And as soon as the voltage goes down again, we disable the brake resistor, and the operation continues as normal. Now, the way that it's very important that any power supplies that we put on this PCB are able to deal with large fluctuations in the input voltage, and there's going to be a lot of noise from the switching of the MOSFETs and from driving the motor. So we need to have large capacitors on the power lines, and we need to take extra care to make sure that this noise from the power lines doesn't get into the power supply of the microprocessor. That's going to be something for the next videos. In this video, I'm just doing a little bit of planning, sort of what is going to go on this PCB, and what components am I going to use, and what do I need to consider. So let's see. We also need Hall sensor inputs. So let's just finish this brake resistor. Brake resistor. And brake resistor is going to be connected like this. Let's see. I just need to add a little bit of, let's see. So there will be current sensing also, going from the MOSFETs to, this is ridiculous. The way that, is there no way to drag the arrow like this? Let's see. Yeah, that's better. That's good. So this would be current sensing. Then we have, what else do we need here? Let's see. So there will be, as inputs to this board, the way that this board is going to communicate with other external devices, primarily the control unit, is going to be through multiple interfaces like CAN. We'll have CAN to B, and we're going to have CAN FD. There will be two interfaces for CAN. Just because we have two interfaces in the STM32, so there's no reason not to expose both of them. And there will be also, let's see, and there will be EtherCAT. Can I change the size of the canvas here somehow? Page setup. Let's let's make it an A3. That's better. So EtherCAT is going to be connected to two RG45 plugs with just normal RG45 plugs. I was just thinking if I would do any kind of power over Ethernet thing for this board, but I don't think I'm going to be doing that. I think that it would be too much to put power over Ethernet injector in this board. It's going to have to be a separate circuit. Because I have a few boards that are going to be driven over power over Ethernet. So I've been looking into implementing the injector circuit for power over Ethernet. And that's something that's going to be going on a different board. So it's going to be two of these RG45 connectors. And the reason it's two connectors is because the way that EtherCAT works is it automatically forwards the packets that come in on the first connector into the second connector while processing them on the fly. All of this processing is done by an EtherCAT slave driver. So we can go to Mouser and see if we can find an EtherCAT slave driver. Let's just search for EtherCAT slave. There is a particular chip that I was thinking of using for this solution, but I just have to find it. Could it be, let's see. Yeah, LAN 9252. That's the one I'm going to be using for this solution. This is a fairly complicated chip that has multiple interfaces for communication with the MCU. Let's see. It has, I think it can communicate both with Ethernet, MII interface, SPI, like normal SPI, 4-lane SPI, and possibly something else. When I'll start drawing the schematic, I'm going to be diving into these datasheets in more detail. For now, I just sort of taking care of the large picture and just picking the components that have the best chance of fitting this application. And it's quite possible that when I start actually drawing the schematic, I will discover that some component may not be suitable. So it's an iterative process. But I'm quite liking what I see in this datasheet so far. I think that this chip is definitely something worth trying. I've never used this chip before. I've never even used EtherCAT before. Because I'm usually using CAN for any kind of motor control applications. CAN has been very good, very very common in many systems, but some people or some companies right now are looking into using EtherCAT instead, because it has lower latencies and much bigger bandwidth. You're communicating over 100 megabit per second instead of just 1 megabit per second as you have in CAN, or even 5 megabit per second in CAN-FD. It's still not really at the same level. But the biggest disadvantage of EtherCAT so far has been that it's been quite complex to implement an EtherCAT solution. So diving into this alternative and adding it as an extra interface on this board would provide a good platform to test EtherCAT and to see what it can do, and to see if there is any continued interest in using it for motor control applications. So I'm definitely putting this chip on this board. I think it's going to be something that's going to be very interesting to evaluate. So I just want to see what interfaces it has to the MCU. Let's see. Should be somewhere in the beginning. Let's see. It has EtherCAT slave controller. Does it actually have a, let's see, does it actually have MII interface to the MCU? Because if it has an MII interface, we could connect it to the Ethernet controller inside the STM32, which could provide better performance. But if it only uses SPI, then we'll have to go with 4-lane SPI instead. Let's see, local bus. Yeah. MII, SPI, digital I, GPIO. Right. So it even supports different network topologies. Very interesting. I'll have to read through this datasheet and try to understand it in detail when I'm going to be laying out this circuit for this chip. So it has port 0, and apparently the port 0 can be used as an MII interface that goes to the microcontroller. Very interesting. So LAN 9252 goes on the block diagram here. This would be two pluggable terminals. So I'm going to be using pluggable terminals, screw terminals, for most of the connections, because that provides the best. It makes it the easiest to connect possibly incompatible cables to this motor drive. So I'm not going to be putting any specific connectors that are for specific motor anymore. I'm going to be putting more generic connectors. I can look here. Let's see. Plug. In Swedish they're called pluggbara terminalblock. But let's see if we can change this to English. That's better. The cookies message is the most ridiculous artifact of the old internet that's still around. Like, all the websites use cookies, and they still have to tell people that they use cookies. Absolutely ridiculous. I thought that was ridiculous from the moment they sort of started with that kind of regulation. I think, like, cookies has nothing to do with privacy. Like, if the website can remember the fact that you have visited that website, that's pretty much what every single website does. Let's see what we can use for CAN. It would be like a 2-position, 2.4 millimeter, because it doesn't have to support any high currents. And then let's see. see what we have here. So possibly something like this. This is very, very nice types of connectors. But I want to pick something that has screw terminals on the plug. So for on the plug, let's see. This would be a. I think this is a plug. Yeah, this is a plug. Let's see how this plug operates. I think it has a crimp terminal. Probably says here. No, it's like a. Let's see. It's a crimp terminal. Yeah. So I'm gonna go and continue looking here and see if I can find something that has a screw terminal. Nothing that has a screw terminal. 2-position pitch. I think the screw terminals are a little bit wider in pitch. We can, the way I can do this, I can search for a plug. Let's see. So, termination style, screw. Connection method. Does this include any? Okay, that's just 8 results. That's nothing. What else could we pick? So I guess the termination style is for the way that it is mounted. So we're going to have a through hole connector and connection method screw. Let's see what we get. So this is better. This is pretty much the type of plug that I had in mind. They're pretty simple and very easy to install. All you have to do is just cut the wires, put them in, screw in screws, and just plug the whole thing in. And you can unplug it anytime, which is very useful as well. So this is 2-position and it's 5 millimeters, and we have 3.5 millimeters. I actually have a few of these plugs that I ordered from China. I want to see what pitch they have. So I have a connector that has 3.5 millimeter pitch, almost exactly 3.5 millimeters. So the 3.5 millimeters is actually a very, very good plug. Most of them are 5 millimeters. I'm going to be using very similar connectors for the motors as well, but they're going to be 5 or 7 millimeter pitch because they're going to have to carry at least 20 amps. For this, I will probably use something like this. So this is a 3 terminal. Over here it says 2. So in terms of current, this is probably a bit of an overkill, but in terms of ease of installation, this is just perfect. Okay. Yeah, so this is just the same data sheet for all of them. 2P to 6P. Great. And then I can just click on this product and I can look in the suggested, let's see, are there any suggestions? Customers also purchased. Maybe it's this. Like the corresponding terminal block. So let's see. We do like this, 2-position. This would be. It's interesting they call it a fixed terminal block, even though it's a pluggable terminal block. Okay. Let's see if there is any PCB connector. I think it's going to be probably something like this on the PCB. Going to be a terminal block that just looks pretty much like this. And the cable can easily be connected to it. Just want to check also if there is any, like I have a few of these similar terminal blocks, and they're quite stiff when they're connected, but the biggest disadvantage of them is that they don't have they don't have any anything that holds the connection in place. So if the cable is pulled, the plug can actually loosen up, which is a bit of a nuisance, which could be a little problematic. Ideally, since this is a motor control application, I want to have something that is held with screws, and I want to have a plug with screw terminals, but I want the whole plug to be held with screws in the mating connector on the board. And I'm pretty sure they have those connectors, but I just need to find them. And I think that they're a little bit bigger. It's quite possible that there are no connectors with less than 5 millimeters pitch that have the screws. Here are a few. So if you look at these plugs, they have screws that enable them to be screwed on in place when they're connected to the PCB, which is very useful. And these ones have clamps around them which hold them in place, which is actually interesting, like one of these. Could it be like one of these? It's also worth. They don't have that many in stock though. I guess they're not very popular, these plugs. And they're also slightly more expensive. But I want to check what this is. So so this looks like a clamp connector for the wires. And it needs to have a proper mating plug or the actual connector that goes on the PCB, which supports the holder that this plug has. So can I see more information? There's actually, in the mobile version, there is a section here where I can see like corresponding terminal block for this plug, but I cannot see it here. Could it be this one? This one seems to have some little teeth on the side there. Yeah. Well, this looks like something that we can use with the plug that I just looked at, and this is 3.5 millimeters, which is very nice. So this is exactly what I'm going to be using, but for the plug I want to see if I can find something that has screw terminals. This is screwless, but it would be nice to have screw terminals. 25 alternatives. So all the plugs that have screws, they don't have the right. So there's one like this. Otherwise, this could be a good alternative, or something like this that just plugs in and then you just hold it in place with screws. I'm gonna have to do a little bit of research and find something that fits the purpose. So I'm not gonna drag on looking at different connectors. I'm just gonna put in here that this is gonna be a terminal block, like screw terminal. It's a little bit too big for the interface. Like plug and screw terminals, they're usually designed for higher currents, so they're quite large in size. But since we're not going at really high speeds, it's okay to use a terminal that has slightly bigger pins. If it was a 100 megabit interface, then it would be problematic to use a terminal like this. Let's see. So besides CAN, this is also going to have a USB, and it's going to be a USB. Let's see. This will have. I'm thinking if this would have a USB OTG plug or a normal USB plug. It could be useful to have an OTG on-the-go plug, since the STM32 supports on-the-go. The only disadvantage of using an on-the-go plug is that it can be harder to find cables, which is going to be changing since a lot of mobile phones now use on-the-go. On-the-go is a little bit bigger connector, so it's round, and it doesn't matter which way you plug in the plug into the on-the-go connector. You can plug it in both the right way and upside down. It doesn't really matter. I will probably use an on-the-go connector, but I have to do a little bit more research and have a think about it, whether it would be useful. Then it's also gonna have a debug interface here. So USB is really just built into the STM32, so really this box doesn't represent much on the PCB besides the ESD protection for the USB port. Debug would be a pin header. The debug port contains JTAG and a UART interface, which can be used to access the console, which is run by the software, which I'll run on the STM32. which allows easy configuration. Talking about the configuration, we also need to have some way of saving the saving some settings. And I'm thinking if I need any EEPROM, or if I can use the some other component that has a built-in EEPROM with a few bytes that I could use. But I think that it's pretty safe bet to put an EEPROM here as well, because we are going to need to remember things like can open address, possibly the overcurrent protection settings, and many other things in here. A lot of the settings will have to go somewhere, so putting an EEPROM would be a good way to handle the saving and restoring of settings. What else? In terms of the interfaces, I think it would be very good to have possibility to control the speed of the motor using just an analog signal. This is useful because some systems may not have a control PC that's going to control the motor controller, and instead just want to control the speed of the motor. And having a simple interface like that is quite useful. So I will put analog interface here. And in fact, it's going to be both analog and possibly the PWM input of 5-volt PWM. So it's going to be 5-volt analog and 5-volt PWM. Let's see. And I think the best way to structure the connections for this interface is that we want to allow, we want to have the ability to plug in potentiometers directly to this interface. So we need to be able to plug in two connections for the speed control, for example. We need to have a ground connection and the signal connection, so we can just plug in a potentiometer in between those two. I think this would be multiple screw terminals where each is responsible for a specific function. So we need to have 5 volts is the most basic support input of 5 volts, but it could be useful to support, for example, for brake input, it could be useful to support up to 24 volts, to have protected inputs up to 24 volts, because some systems use 24 volts as the main the main supply voltage, even if they're running on 48 volts. it's not that uncommon to use 24 volts as the voltage for proximity sensors and other types of safety systems. So speed, brake, this would be both analog. It's quite possible that these inputs could be connected to the same pins on the STM32. I'll just have to see if I can find any suitable pins that can both be used as an analog potentiometer input and the PWM input. Then brake would be just the GPIO input that will go to the brake hardware on the STM32. The STM32 has a dedicated brake input that will stop the switching of the MOSFET stage. So this has to go to the brake input. PWM is going to go to PWM. Direction change of the motor maybe. That would be good to have here. Unless we control that with the same input as the speed, which could be configurable. So we can make the software configurable so that it can support both. Let's see. We'll have the brake resistor out here. Possibly like yeah. Brake resistors are typically a rather large resistor that has a low resistance and ability to dissipate a lot of current, a lot of heat, a lot of power. That'll be the correct way. So it's a low resistance resistor in a metal package that gets screwed onto some large metal surface on the frame of the machine. So direction change would be one thing, and what else? Wonder if I need any switch to set the CAN address. It's quite possible it's actually just a waste of PCB space. I can use EEPROM for that. So I can also, when using CAN open, I can also use the protocol for identifying new devices to set the CAN address. But the only thing is that it's actually quite useful sometimes to set the address of a new board that goes into the machine to one specific address when it's being installed. So it could be useful to have a switch for the CAN address. I'll put a small dip switch there so that at least some bits of the address can be preset using the switch. No, let's see, copy this, come on, copy paste, yes, good. So this has now become a combination of both the interfaces, and let's see, put this here. gonna keep this side just for the outside interfaces. Technically this would be an outside interface, so this goes here. But the EEPROM goes on the STM32 and with the STM32 there. I'm being a perfectionist. Let's see. So we want to connect the brake resistor. We have encoder. Let's see. Yeah, I can put some text here that says encoder. And in fact, this board is going to support 2 motors. So we need to duplicate all of this. We can use the same brake resistor. So let's see, let's put this up here. We can use the same brake resistor for dumping energy from the supply lines, but we're going to use 2 different power stages. And also then we can connect 2 more proximity sensors. So this will just go up. Let's see, so this will go under here. And then the brake resistor goes under there. This is going to be a bit of a challenge to drive 2 motors at the same time. I'm pretty sure it's going to be possible by using both timer 1 and timer 8 on the STM32, but it can still be challenging. It's not something I've tested before to be able to measure all the currents and do it all in real time on the same chip. But it's going to be an interesting way to evaluate this, the possibility of using the same STM32 to drive 2 motors. Let's see what else. What else could we need here? I've completely forgotten the Hall interfaces. The Hall sensor interface is very important. Can't forget the Hall interface. Can put the Hall interface here. And it's quite possible I would need to use some level shifting for this if this is going to accommodate all varieties of Hall sensor signals. But I'll have to do a little bit more research on that and just see if it's worth it. If it's not an issue to use just 5-volt inputs, I will just have simple circuit that supports 5 volts on the inputs and clamp it to 3.3 volts. And it would actually be better if I move this up here. I'll just move this here. No. The incredibly annoying way of creating arrows. Can I remove that part? It won't allow me to remove that part. Is there a way to remove that part? Can I actually move this? No? Yeah? Yeah, it was possible to move that, but then like I have to somehow make sure that this last part doesn't result in a bend. Let's see. Come on. Okay. I guess there is a small connection point there, so it's much easier to just connect it like that. And this goes here, and we can just swap places on these two cables. So. Come on! No, I don't want that. I want this to go here. Kind of like that. That's better. And then this one will go. Let's see. Yeah, that's better. Cool. So, Hall sensor inputs are taken care of. And then I'll just copy this section and place it here. So 2 motor drivers, 4 proximity sensors, Hall support for both motors, an EEPROM for saving settings, possibly a serial interface that is more like the traditional RS 232 interface, possibly. Although that increases the BOM cost, and since I have both CAN and EtherCAT, I don't think that it's really necessary to have the traditional serial interface. Although there will be an expansion interface. SPI, I2C, and UART that will connect to a pin header. So if it's ever necessary to use the UART to communicate with this board, then it's I would guess that whoever is going to be using it would have to have a converter for the RS232 to UART, and that would make it easy to connect. At least it doesn't rule out the possibility of connecting a serial controller to this. And SPI is very useful for any simple expansion that one would like to put on this board. It's good to have it on an expansion port, as well as I2C. So the way this board is going to be used, primarily, the application I'm designing this board for is going to be probably using CAN or EtherCAT, and it's going to use the 4 proximity sensors to sense when the motor reaches the extreme points, and that's it. So anything else I put here is just me thinking of possible future requirements that that would be good to take care of at this design stage, so that I can use the same board for different applications, and so that I don't have to redesign the boards. So there will be a 48 volts power supply, so we need to put a power connector here. Amps plug. This would be a slightly more heavy-duty plug. It's gonna go to the MOSFET drivers, MOSFET power stage, but it's also gonna be connected to a regulator that will go on the board here. Something like in the range of 1 to 2 amps maximum. Maybe 1.2 and 40 and 5 volts to 3v3. This would be something like maybe not more than 1 amp, because STM32 doesn't really take so much current. For the 5 volt line, it could be useful to have higher current capability, because the 5 volt line is going to be connected also to the encoder interface here. And that will drive a potentially unknown encoder interface inside the motor. So having a little bit higher current capability is good for that regulator. But for the 3v3 regulator, the voltages that it generates on its output are not going to be used outside of the board. So that would be maybe like 500 milliamps. I'll have to have a think of how much each part is going to draw, and then just make a educated guess of the regulator I'm going to be using. Let's see. So this will go here. This connection is important because this is the power line that's gonna behave a little bit differently from a typical power line. First of all, it's gonna exhibit a voltage rise when the motors are braking, and it's also gonna exhibit a lot of noise from the switching of the inductors in the motor. So this will have to be handled in a little bit special way. But in terms of regulators, I think this would be pretty much the way that I'm going to set it up. Quite possible that I may translate this to 12 volts first. I'm going to have to check if there is anything that needs 12 volts. Then I may use a 12 volt regulator plus a 5 volt regulator. But for the sake of this diagram, I think this would be enough. What else should I consider? Speed, brake, direction. So for these inputs, it's going to be, it could be both speed and torque. Let's make sure that this says also analog. Analog and PWM. And it's going to be programmable from the debug console, whether this is speed or torque. Right. So brake input will allow us to stop the motors. Direction will change direction, speed, torque. We'll have to implement ramp inside the software in the STM32 for the acceleration ramp, deceleration ramp, and speed ramps, and any similar functionality. Encoder will allow us to implement positioning mode for the motor. Specifically, the zero pulse input is very useful for the positioning mode in the motor. Proximity sensors will allow implementing position mode that can span multiple revolutions, and also finding the 0 points. That'll be the job of the proximity sensors. Did I just move away the EEPROM? I think I copied I thought I copied it, but I then moved it. So EEPROM goes there. And then I think it's pretty much what's going to go on this board. This has to be focused on motor control. It cannot contain anything like SD card or anything like that. It's not going to run, at least in the usual situation, it's not going to run any user application. It's going to be just focused on controlling both motors. But what's important here is that it has the interfaces that allow it to be usable with different systems, so that it can be plugged into an existing system without having to add too much extra hardware. Let's see. USB is also useful for a high-speed connection to the computer, specifically when tuning the driver, because we want to measure currents at a very high speed, and USB allows us to transfer the data in real time to the computer and monitor what is going on with the motors when we change different parameters. So it's very useful to have a high-speed connection to the computer. Debug interface provides programming, and UART, simple serial port interface to the STM32 chip. Yeah. And this dip switch allows setting CAN address when replacing a board. Expansion. I think one thing that is important also here is to have a heatsink and a fan. Sorry. So this would need to have heatsink and a fan, and they would need to be connected to appropriate input on the STM32. gonna move it over here so that it's kind of like two separate blocks. Temperature sensing, I'm trying to think if there is a temperature sensor in the DRV chip, which I think there is, but it's also useful to have a temperature sensor on the MOSFET, on the close to the actual power stage. So it's going to be like a temperature sensing resistor that will just sit very close to the MOSFETs. And I have to have a think of whether it's going to be enough with just one per stage, or if I would put one sensing resistor between each, or at least on two of the MOSFET stages, so that if any one of them, or actually probably on all three of them, because they can still short even if it's just one stage. So if both MOSFETs for some reason open up at the same time, they can still be a short circuit, although that would be protected by the DRV chip. So the DRV chip will power them off if there is too much current. But they can still get hot though if the dead time configuration on the PWM is not optimal for the MOSFETs. So if they happen to open up too soon after one another, then they will heat up. So we still need to have some sort of temperature sensing on the MOSFETs. Right. So I'll put temperature sensing here. It will be readable over analog inputs on the STM32. And can put the heatsink. And the fan here. So temperature sensing is taken care of. And anything else that could be useful to have here. Let's see. I think this is enough for now. I think that I will go over this this high-level diagram and translate it to schematic. And when I'm going to be doing the schematic, I'm probably going to come up with other things that could be necessary for this board. But in terms of the high-level schematic, I think this is pretty sufficient. We could add also fault output. So if there is any fault, we can output it here. That's also very useful to let the rest of the system know that something has happened. And this is going to be useful for only for the simple control, because both CAN and EtherCAT have built-in ways of reporting faults. So in terms of CAN, it's going to be a fault frame, an error frame that's going to be sent by this device, and for EtherCAT it's going to be a similar solution. But for the simple control, we would need to have a fault bin. And obviously all of this has to be times 2. Because it's going to be for both motors. I don't like the fact that this one is smaller than the heatsink box. Let's see. Fan. That's better. Okay. I think this is pretty much it for this. God damn it, somebody's messaging me. I'm working now. I can't answer any messages. What else? What else? What else? I think I'm gonna leave it at this implementation plan for now, and let's see. So this would actually be 40 amps though, because we have 2 motors, so we need to support 40 amps. So anything that's gonna serve as a connector there is gonna be 40 amps, and this would be power stage 20 amps. So I'm gonna go for the 20 amps typical current requirements there. When it comes to higher voltage motors, they usually don't exceed 10 amps, because you can generate a lot of torque with up to 10 amps. It's only when you have lower supply voltage that you need to handle higher currents, because to get the same torque at lower supply voltage you need more current. So I'm gonna have to see what type of heatsink. Heatsink is actually a very important part here, because heatsink will determine the placement of the MOSFET stages. So depending on the type of heatsink I can find that can cover both, or that can cover at least one of the MOSFET stages, it's gonna dictate how the MOSFET stage is gonna be placed on the PCB. Right. So that's it for now, and next step for this PCB is gonna be actually diving into designing each one of these parts. Thanks for watching, and subscribe to my channel for more PCB design videos and electronics design. And sometimes I do live streaming. Well, this is a live stream, but sometimes I do also live streaming of my dog and dog training and a few other things like. But I hope you got something useful out of this, and stay tuned.